software is there in combustion vehicles and it is much required. But yeah, like you said, there's like a much broader range of what do you say, functionalities which an electric vehicle needs to comply with and adhere to compared to a CV software. Okay, so as it's written here, while CV software primarily focuses on optimizing combustion vehicles and vehicle dynamics, electric vehicles go beyond that. And it's due to the electric powertrain, as you said, there are a lot of control functions. So what all is there in the software of electric vehicles? We'll look into that. So like you said, there's the motor controller which monitors and regulates the functions of the battery and the motor. And this is controlled completely by software. Like there is a hardware component to it. So that's why this is where the embedded software comes in. So aside from that, moving on, we can broadly classify the softwares used in electric vehicles into safety, utility, maintenance, connectivity, and assistance. We look into each of the following components in detail. So, like for safety, what is the first thing that would come to your mind? Like, I'm pretty sure all of you have heard of like battery fires occurring recently, like in Teslas and overcharging issues, right? And then same, like as you said for utility, it's like necessary to control your motor, else like your car is not going to run. And same with connectivity, like all the components of your car need to be in constant uh, contact and communication for efficient running, right? And yeah, so first we look at the utility. So this is how a motor controller works. Uh, we'll not get into the details here, but like essentially, you have a battery pack which is giving you a DC voltage, correct? And your motor which is working on an AC current, an AC voltage. So between them, you not only have to convert the power, you also have to like, see, you could just essentially convert a power to a fixed value, but you have no control over the speed or the torque which you're getting from your motor then. So that's where the control comes in, and that's what the motor controller does. So most controllers work on the logic of like based on the inputs and all which you provide according to like how much acceleration is desired. Uh, the motor controller sends a voltage to the motor. But at the same time, like any control system requires a feedback, right? So do you think voltage is a good point to use as a feedback since that's the output? Or like what else could be used aside from voltages? Like something, some other component which you could measure. Yeah, correct. So we'll be using current as our feedback system. So the current which is given to the three lines is sensed and then calculated, and then you get your feedback, and accordingly it's controlled. Moving on to the battery management system. As I said about the vehicle fires which are erupting very frequently nowadays, one of the major components which it happens is because of the battery pack overcharging or like basically operating outside of like limits which it's ideally supposed to operate in. Okay, so what a BMS essentially does is it monitors the working of the battery, like what is the current it's working on, what is the voltage at that point, what are the temperatures. Overheating is also another factor which can cause issues. So based on these factors as inputs, it outputs like if there are any errors in any of the three components which need to be monitored. It'll give you a warning and essentially ensure the safety. Okay, coming to like the biggest thing, we talked about communication. So what all do I mean? As you can see in the picture, like almost everything in a car can be analyzed and all the data can be collected. Like you can see here, it's a race car here. So most essentially, like in terms of performance, if you guys know F1 cars usually end up having like the most need for like perfection in terms of everything. So hence, like I feel, hence they need all those sensors. It's mostly a lot of times during the testing phases where you can collect all the data and then improve on stuff. But like let's look at some of the sensors which we're using. So For each wheel, you can use Hall effect sensors to get the speeds. Then you have temperatures for brakes, or like your brake pressure sensors, exact position, so that you can use like a LiDAR or something. And at the same time, you have sensors to analyze the flow pressure and everything for the aerodynamics. And there's many more. So overall, you can essentially gather all that data, and then it's all on you to process it. Now here are two things. One is you can collect the data and process it at a later time, but also at the same time, if you've seen any F1 race, there's usually someone who's gathering like real-time data and analyzing it. That's also a very big requirement in the field, because any faults which occur could be like warned there, and you can communicate with the driver for a better running. So that's where a lot of competition takes place. Then, as I was speaking about the assistance, so you guys might have heard of like advanced driver assistance software nowadays. So, like, why is it important? Okay, so like you guys might have seen like people end up like driving in like very little sleep or something, or like even when you're normally driving, it's very easy to like succumb to human error. So it's like a system to help you out and give you warnings in case of any issues. Okay, and more importantly, it's actually an additional safety feature. Okay, so like if you look into like each of these mentioned here things, so adaptive cruise control is basically like it uses sensors like LiDAR and radar. So to basically understand like the positioning of the car around, and then like if you're slowing down, or basically it ensures that there's a smooth running. Same for anti-lock braking systems. It's something which is used more in CVs than EVs, because they have their gear system, and when you brake, your car tends to stop. So it's for like understanding when there's a sudden brake and like keeps the car running. Same for like collision avoidance or like blind spot. Again, it's sensing like the objects near it and warning the driver that there is an issue. Then for lane departing, you can obviously end up like departing on your own. Like it could be an informed decision, or it could be like accidental lane departing. So that's where like software comes in. It like assesses the situation. It sees what situation it is. That's why like you taken all the ML of it. And then again, park assist. So you do perpendicular parking, you do parallel parking. A lot of times there are issues, and you don't always have someone to like look behind. So it's something which helps with like what do you say, which direction you should go and all. So that's that. And like if you see, these set the foundations for like the upcoming boom, which is going to be the autonomous driving. See, first you start by assessing the driver, and then you become the driver. So software starts out here, and it just moves on. So now looking at the main topic which we'll be looking at today, SOC. What do you guys think the full form of SOC would be? Yeah. As you can see, like fuel is for combustion vehicles, state of charge is for electric vehicles. Like even in your phone, you have your percentage of battery, correct? But now here's the biggest issue. We cannot tell the SOC, like it's not a given fixed thing. It's something you estimate. It's not like this is definite. There's no answer like that. So mostly today we'll be looking at like different methods of estimating SOC. So like firstly, as we've written here, one cannot tell if the battery will be overcharged. So that has led to like most of the battery fires, like they don't occur when the car is like on a standstill or when it's running. It's mostly occurring during like charging. So ideally when it reaches like the 90 or 100, you would ideally stop charging. But if the SOC estimation is not correct, it would stop charging then. And then secondly, range anxiety. Yeah. So have you guys heard of like a lot of Uber taxis and all like switching to electric, and then like coming up with issues like the range is predicted to be some 20 kilometers, and like within 2 kilometers the car stalls. So that's another issue, which is because of not estimating SOC. So if your SOC estimation is correct, technically your range estimation would also be correct. Yeah?
I just want to make a clarification here. One part of a charge is the capacity to hold the charge.
Yes.
And the second 20%, you might have 50%, which is actually 40% of the original charge.
So that is like about the state of health of the battery. It deteriorates with age, but like even if it's at an 80% of original, if your battery is ideally charged to 100%, that 80% has become 100% for its current life.
So that I understand, but when you say SOC, it is the 80% being charged to 100%, that 100% is the SOC or the 80% is the SOC?
SOC is the state of charge. It can be at any percentage.
As in it is the.
It's like like your phone battery. It shows like different percentages, right?
Okay.
That is your state of charge of the battery.
And the other thing is what we call as state of health.
Yes. That is like a long-term deterioration.
So is there some content that you have later on state of health as well?
No, but if you have any doubts, you could ask us later. Thank you. So then the third point here is you cannot determine the age of a lithium-ion battery. So like if you bought an electric vehicle, you don't want to ideally just run it for 2 years and like have to change your battery pack every 2 years, right? You would ideally want it to last like 4 or 5 years, right? So that is another thing. If you estimate your SOC properly, you'll be able to maintain a healthier battery life and most probably be able to retain the same battery for a longer period of time. Thank you. And Prajwal will be taking on from here.
So I'm Prajwal and I'll be taking on over to see the types of SOC estimation techniques. So just as background, just to re-emphasize, we realize why SOC estimation is quite important. Not only do we want to know how far a car runs, this is critical because there's something called SOC limits to a battery pack, which means you operate it only between say 10% of the SOC and 90% of the SOC. So if you're like say charging the car, you don't want to cross that 90% because if it crosses 90%, there's a situation called overcharging, which may lead to something known as thermal runaway of lithium-ion batteries. Because what happens is basically there are some side reactions apart from the main reaction that is responsible for storing charge that can feed into each other. Like say a nuclear reaction, it can feed into each other, and what happens? Kaboom happens. So you don't want to reach that stage at any cost. So knowing exactly where you are on the SOC line is highly critical to us. It's important to our life as well. So now let's move on. Now we'll go on to the first method and probably the oldest method since the advent of lithium-ion batteries. This is called direct measurement. So how do you guys think we can tell SOC? Like just on a glance, how can we tell how much charge is there in a battery? Any idea? Voltage level. Okay, so I might not know how exactly it looks in the middle, but you know the maximum voltage will be when it is at full charge, and at zero charge the voltage is going to be minimum. Mostly it is zero. Okay, lithium ions have zero. There are other chemistries which may have different minimum levels. So yeah. So this is the most basic way that we get to know what the SOC of a battery is. So as you can see here, you monitor the parameters V, Z and T. Now V is clearly voltage. So you can measure the voltage of the cell at any point and then cross check with something called an SOC OCV graph. So that is a very characteristic thing not only for a battery but for that particular chemistry, right? So what you will do is you will measure the OCV and then draw a line till there and then drop it down again and then you will get the SOC percentage. So that's how you go about and these graphs are made in laboratories where they are very accurately measuring SOC. So these are the standard way of going about it. Now can you guys tell me why we will ever need Z? First of all, any guesses on what Z is? Impedance. Very good. So that is the impedance of the cell. Any idea why we will need impedance if we are using this graph to the T? Okay. Anything else? Sorry. That is a very good point. So actually SOC is a function of many different things, not just voltage. It's a function of temperature as well, and it can depend on the impedance as well. But say we ignore the fact that it depends on all this, say it's a function of only voltage. Even then I'm saying we might need Z. Any idea why? It's a small technicality that when I keep saying voltage, I mean some particular kind of voltage. Any clues? So do you guys know what OCV stands for? Sorry? Open circuit voltage. So what does open circuit voltage mean? Guys, any idea? Yes, there is no loop in it, in which case there is, what is zero? Current is zero, right? But when we are running a car, can we expect the current to be zero? No. So this method, if you just go by this graph and measure the voltage across the battery, you are going to get some error, because we know OCV is not the same as terminal voltage in activation. So how can you fix it? Impedance creates the error, and
that's the current we are assuming that at this stage this much amount of the current might go and that we calculate.
yeah. So can you like summarize that into a formula? It's a very basic equation that you might have come across. Yeah, V equal to IR, but more specifically, if I were to say, I would say the EMF of the cell is equal to the terminal voltage plus current through the cell times internal resistance. Have you ever come across this? Where you have a real cell with internal impedance. So way you calculate that is EMF minus IR is equal to VT, terminal voltage, right? I won't be able to draw here, but yeah, that's, you must have seen it quite often in many places. So that's the idea here. That's the reason we calculate impedance, because it's one more level of correction. We are making it closer to terminal voltage, and from terminal voltage you are deriving open circuit voltage and then comparing it. So that's the simple idea behind direct measurement. And yeah, and again, one more layer of improvement we can add is there are different OCV curves depending on the temperature. So you can have something called lookup tables, where you will like see voltage value, you will see temperature value, and like log tables only, you will like find out the value like this, like go through x-axis, y-axis, cover it, and find the value. Now, what are the let's go through the advantages and disadvantages. It's a relatively simple and widely used method. It very clearly doesn't require any additional hardware or complex algorithms. This is a very simple computation that can be done with very minimal level of software, and it's a quick estimate for SOC, especially during no load conditions. When no load condition is there, even that small computation of EB minus IR is equal to VT, we don't do that. It directly comes out to be EB itself. So we don't have to go for more complex algorithms if we directly can, we know that measured voltage itself comes from this. Disadvantages, accuracy is affected by varying load conditions and battery aging. So it so happens that depending on load, this value changes, and we see error, and that leads to some kind of error. And of course, battery aging, like we told, when we are discussing SOC, we kind of are blind to the fact that the battery ages as well, and there is something called state of health, as she mentioned, SOH. So we are blind to that, so obviously error due to that occurs. And it's not suitable for applications with high power or rapid charge and discharge rates. So any idea why that's the case? Note that I told a formula like something like EB minus IR, but I have written Z there. So there must be something else to the story, right? There must be reactance to the story, right? there's not just resistance to the cell, it also has some kind of internal capacitance and inductance, so it has reactance. So when you're using rapid charging and discharging rates, that is you're varying the current wildly, there is another impedance that comes to play, and that is due to the capacitance, which doesn't come if you're like slowly charging. If you are slowly charging at a near constant rate, then those values are really low, because if you remember, they're like proportional to omega, right? Reactants are proportional to omega. Yes, sir?
I notice sometimes when I charge my phone with a rapid charger, it discharges just as rapidly.
Oh, yes, sir.
So is that something which is related in terms of output?
Mm, it,
So let's say you take your phone and say 15 minutes, 50% charge.
yeah.
It's not a software number that is just showing up, and we're actually 50% charge. And in your phone, it will discharge very, very rapidly as well. Normally, if I charge it with a slow charge, but it discharges much more slowly.
Yeah, I am not exactly sure for why that is the case, but I can tell you one consequence of this. So when you do rapid charging, you can visibly observe that your phone becomes a frying pan. That is true. Yes. That is not because it is rapid charging. Rapid charging is an algorithm. It's not exactly about just pumping in high amounts of current. But when you are doing rapid charging and you're trying to increase SOC quickly, what happens is you also have to overcome these impedances. And you have to overcome impedances, you have to pump in extra current. So that's one of the reasons. So the resistance also is encountering more current, so it's going to heat more. So that's one consequence I know. I will get back to you on what exactly is the chemistry behind this phenomenon.
State of health of battery also changes if we use it. Like if we do rapid charging or it remains same as
Yes, yes, definitely. So when you're doing rapid charging, what you're basically doing is abusing the cell. Right? You're supposed to use the cell with love and affection. You're not supposed to pump out things, but that's useful for us, so we do that. So whenever you have high rapid charging and discharging rates, your state of health decreases more than it would if you were charging it, especially in the case of lithium ions. And then there is also this fact about limited accuracy during mid-range SOC values. So the reason for that is, if you take a typical, this is a representational SOC OCV curve. So if you take a typical SOC OCV curve, you will have a graph like this that starts from 0, and in the middle range from about 20 to 70, it is very flat. You can almost see no voltage change in that region. So when it charges from 20 to 70 SOC percentage, there is very minimal increase in voltage. So think about what happens when you're doing the reverse way. So you're like trying to find the SOC. So you're finding the OCV outside, and then you're dropping a line from the OCV and then dropping down to SOC. Suppose you had a small error in OCV that gets magnified, right? Can you visualize that? So if it's a flat line like that, if it's quite flat like that, and I drop something slightly above it, the distance between the vertical drops is going to be huge. So especially in the mid-range values, small error in voltage measurements can get magnified while calculating SOC. That is the one more drawback. And since we have dissected this enough, we'll move on. This is called Coulomb counting, and in a way you can say this is the definition of what SOC means. Just from the name, can anyone guess what Coulomb counting is? And it's also on the screen. Yes. Yeah. And how do you find the charge? But see, it's not really a linear capacitor, so you can't say Q is equal to CV in the cell. Here you're not wondering about what is going on in the cell, you're only wondering about what is going into the cell. And the very fundamental tenet of Coulomb counting is, I am putting some current into it, and I know that if I integrate that current, I know what charge is going into it. And I am saying if I know for a fact that it's at 0 SOC, and like say I'm pumping this much charge into it, I can get back that much charge out of it. That is in essence what Coulomb counting is, and as you can see, it comes down to the very point of what state of charge is. It's literally charge. You're calculating the charge going into it and you're calling that as the amount of charge in it. Sometimes it's also called bookkeeping for reasons that are historical. Yeah. So, what is the problem with this method? Problem with this method is error is cumulative. Especially in current sensors, what happens is your current sensor always overestimates or always underestimates. So when that happens, you're integrating some delta. So the error keeps increasing linearly with time. Does that make sense? Say I am putting in a current of 5 amps, but I measure it as to be 5.1 amps. So in 1 second, the difference in charge is 0.1 coulombs, right? In the next second, the difference in charges will be 0.2 coulombs. So it keeps increasing. So this is a cumulative error, and it is very highly dependent on how good your current sensor is. Yeah, so typically when you are doing coulomb counting, you will also again use a lookup table and then correct it with respect to the OCVs and such. Let us look into the advantages, since this is a very straightforward method. It also has very low computational requirements. All you need is an integrator, which is from software very easy to implement, and it can provide reasonably accurate SOC estimation under ideal conditions. It's ideal in the sense if your like current sensor is pretty good, the SOC estimate is for the amount of effort you're putting, the SOC estimate is quite amazing. Coming to disadvantages, like I told, it is very susceptible to the inaccuracies in current sensing. If you have some error, it integrates in time. And then it requires periodic calibration to maintain accuracy, because like I told, the current sensor, this is again it's like a fallout of the first point. If you have to periodically look at the current sensor, see if it has any error, and see if the SOC calculated by this and SOC estimated by any other method are the same, and then recalibrate it, because it tends to stray down away increasingly in a non-decreasing fashion. And then accuracy can be impacted by temperature variations and battery aging. This of course is true for most methods, but yeah, temperature variations can always be accounted by different methods, which we will see now. So this is a relatively simple method. I mean, the past two have been relatively simple. Now let us look at more modern algorithms to calculate SOC. Okay, this is the usage of a Kalman filter. It's probably overwhelming, but don't get afraid. We'll try to understand this at least in a broad level of what's happening. So the first thing you understand is something called a model of a cell. What is a model? A model means you are trying to get the voltage current characteristics of the cell using some resistors, capacitors, inductors, diodes, whatever. Using components we know have some typical voltage current characteristics. So a second order RC model basically looks like that. It looks like an ideal voltage source, then has an ohmic resistance, and then has two pairs of resistors and capacitors in parallel. Each represent different things. Yeah, and they have pretty standard values for most lithium-ion cells. Now, now that we have this model, it's all going down into math. So, so what you're going to do is you're going to construct some state variables. What is a state variable? It basically represents what is happening in the cell at that moment. You guys have any guess for what state variables we can choose? So the state variable here is x, okay? It's on the right side. Any idea for what state we can choose? Like, what do you think represents the state of the cell? Like, what parameters that are like purely internal to the cell? True, but according to this model, we will treat that as a constant. So it doesn't change with time. I'm asking something that changes as you move along, but it is intrinsic to the model itself. Can I say SOC is one such thing? SOC changes, but it purely depends on the cell. It is contained within the cell. It is a property of the cell, right? So SOC is the first key state we will use in the state model, and in fact X is a vector of dimensionality 3. So we will have, as you can see, these are like 3 cross 3 matrices and a 1 cross 3 matrix, 3 cross 1 matrix. The other two parameters that we will be using here are the voltages V1 and V2. These also we will treat as entirely contained within the cell, right? So yeah, we construct a state equation that looks like x of k is equal to ax of k plus bu of k, and here x is the, like I told, x is the state, y is the output, and what should be the output of this? We will call the output as voltage. So I'll tell you how that works in a while. So we call y as the output of the voltage and u is the current taken, right? What is G? G basically represents the non-linearity of the cell. We know the cell doesn't behave exactly like this, it behaves like some weird way, and we will call that as G. Now, based on, we can do Kirchhoff laws for these, right? And we can find out the governing equations. From those governing equations, you can get A and B. So that's how A and B have come. RCT is basically R1 and R2 is basically R2. So from that you derive A and B, and that from there on you do something called a guess. I'm saying this is the prediction step. Prediction step is basically an extrapolation of the state equations, right? And here P and Q are the noises in X. In X and U, P and Q are the noises. Now this is complicated. There's no point explaining exactly what this is. I wish I understood it myself. But yeah, the fundamentally what is happening. So you have like a bunch of equations, and they represent the state. From that, moving on to the next state, you calculate the output variables. Output variables being voltage and current. Now you can measure the voltage and current, right? You can actively measure the voltage and current coming out of the battery pack. But this will predict something else. It will predict something else which initially will be wildly different, finally it will be like slightly different. And you get that error. You have an error in that. And then through the system, you back propagate that error and see exactly how much your SOC had error. So basically what you're doing, you're seeing the error in voltage and then back calculating to find the error in SOC and correct that SOC. And you repeat this every step. In essence, that is what a Kalman filter is. You use a model, predict two things. One thing you can actually measure and find the error. Using that error, you back propagate and find something you don't know. In essence, that is what a Kalman filter is. And just on the screen, this is a very complicated expression. So you can imagine that while implementing it, this is going to be a big pain. So one of the biggest disadvantages here is, first of all, you have to have a detailed battery model. I should know that this model looks like an actual cell. I should know that the voltage current characteristic should be like an actual voltage current characteristic, and it requires very high computational complexity. Doing these calculations manually will take pages and pages. So you must imagine that we are trying to limit the computation in an EV. So this is going to bulk up the computer or like the microcontroller used in the EV massively. And of course it's going to increase the cost predominantly as well. And yeah, and again this filter also requires certain tuning parameters, and those are just some of the numbers here. Those are the tuning parameters. You have to keep tuning them for optimal performance. This is why it's annoying, but Kalman filter is actually a very robust estimation method because every time you run one iteration, you get closer to the SOC value, and the closer you are to the SOC value, the lesser error you will predict and change will be lesser. So you will converge upon the SOC value pretty nicely. Yes sir, this is a feedback loop, but it's not a physical feedback loop, it's a mathematical feedback loop. So we predict an output, see how that output is not far away from our actual output, and then feed it back to find what the input initially was or the state initially was. So that's in essence how a Kalman filter works. It's again very popular for for stationary battery applications. Like say if you're having a lithium-ion battery to power sorry. Yeah, stationary. Yeah. So any examples of your mind? Let's say to power a supercomputer when it's off the grid. Just for the geeks. In those applications, you can afford to have a big computer that can perform these applications. But when you are in a car, everyone like from our experience, we know everyone is struggling to reduce weight. So you don't when metal parts are being reduced are being actively designed to have lesser weight. You can't add a computer in it and increase it. So
we are using a bunch of neurons to calculate the features and then using those features to output certain reason. Like here you have this voltage, temperature, current, everything, and then middle layer it will process and find the suitable weights and edges that will further enhance it, and then we will again extrapolate in the next layer, and then it will finally become an output information.
that is a spot on answer. That is precisely what a neural network is. What is a neural network? It is a machine that initially starts off dumb. It doesn't know physics. It doesn't know capacitor, resistor, nothing. And then you tell it, you feed it something. It doesn't know what to do. It splits something random. And then at that point, you tell it this is the actual value. And then it tunes itself to produce that value. And then you keep repeating this process until whatever system it follows actually becomes very accurate. It becomes similar to a model you use and accurate beyond that. So that is in essence what a neural network is. So yeah, like we told, the purple dots are a bunch of neurons, and they take inputs current, voltage, temperature, average current and average voltage, right? And then there are two layers, and in each layer there is a certain type of computation that goes on, and the output is the state of that. And what do? You train it on data. I am giving an Excel sheet of large number of points where there is current, voltage, temperature, average current, average voltage, and SOC. I am telling if I give this out, input you should give me this out for like very large number of data points. And in fact, we will come to it. We have also tried this and we have done it for around 75,000 points. 75,000 data points which have 6 numbers. Those 5 and the output SOC. So once you do that many number of times, it becomes very accurate. It understands the battery pack very well, and for any random pair of a set of 5 values, it should be able to predict a good scale. I think different kind of neural networks are used. This is something called an artificial neural network. We implemented something called a feed-forward neural network. Just different types of neural networks, nothing much in that. And yeah, the error in this is close to 3%. Just by training to like 25k points, which in the grand scheme of machine learning is very less. You can get this to around 3%. And yeah, what are the advantages? Can you tell me a disadvantage? Like, I mean, it's on the board, but without seeing, I guess. Any disadvantages that you can think of?
Long time to train, data dependent, how you feed them, how well you feed the data.
Yes, exactly. So it first of all depends on the quality of your data. If you measure with bad instruments, you're going to train the model badly. And like you told, one of the most important things is it takes a lot of time. I can't implement this and expect it to work immediately. I can't sell the car after I have implemented this because it's going to give wildly bad values, which may or may not lead to death. So yeah, so you have to train it yourself initially and then fit it into a car so that it can function properly. Also, there is a large amount of. Can you see the lines there? Every line there represents one kind of calculation. So this is just for a very basic network. Actual networks have lots of these lines to store, and thus you can imagine that this is actually it's actually quite heavy in computation, but not as much as carbon filters, but still it is quite heavy in computation. So so yeah, you again have to have lots of computer capability on board your car to achieve this.
We can take the data while it is running and everything, and we can refeed it and refeed it also, right?
Yeah,
that
but
way we can
see, very valid question. So very valid question. When you are training a model for a battery pack, what exactly are you training it for?
Basically for efficiency, how it should take the load and what.
That is true. So we took in a bunch of parameters. Right? Do you think anything is missing in that?
That's a problem, right? You won't come to know what's missing. You only know something is missing.
Yeah, that is true. It's very hard to know what is missing, but there is something distinctive that the missing that we have also mentioned today. SOC, you are calculating SOC, so you can't input SOC to calculate it. It's the age of the cell. So when you are training the model, you are training the model for how it behaves at that age. And as it yes, exactly. So the battery pack itself changes on how it behaves with the state of energy. So it is required that you have to keep training it as well as using it. You can't train it initially and leave it because if we treat the battery pack as a human, the model knows how to handle a baby but not a old man, basically. And you can't expect them to behave the same as well. Yeah, possible. So yeah, that's one of the reasons why you have to continuously train it, and you can't just train in the beginning and let it go. Okay, so just as a case study, I want to talk about the one we use. EMOS BMS is a very popular battery management system that we have used. We use and will continue using. It's popular among other FS teams as well. So yeah, so one of the method that it uses is again typical code counting as an initial estimation, and then what do they do after that? They use neat trick. So I told you when you do code counting, there's a error that keeps increasing, right? So what they do is whenever you charge the battery pack and you know you come to 100% SOC, like the charger decides you come to 100% SOC. The charger decides you come to 100% SOC. You see what that SOC is, and then you see what your current estimate of SOC is, and then you pull it up. Basically, you're just keeping checkpoints every time you charge it to 100%, and then keep pulling it up whenever you put the charge. That's a neat trick that EMOS BMS does. And then there's also a second level of estimation that uses what we saw earlier, the same second order RC model, and uses an SOC OCD curve, and then basically it updates two values, one from the RC model and one from its own Coulomb counting. and then it takes a weighted average. It says, okay, these both are predicting like this, must be somewhere near the middle, depending on which is more accurate. Right? So it does that and then computes. Yeah, so this introduces around 5% error according to this. But seeing how computationally lax it is, 5% error is pretty good, which is why it's a standard. Which is why use BMS is a standard for us. So talking about embedded.
So as Sanjay has explained about what neural networks are and how can we use state of charge to compute neural networks, the problem statement doesn't just end there. Like you can obviously train, let's say, how can we figure out, like looked at a real life neural network, like has trained a neural network or that's all you've done. Anyone else here? Okay, so if you look at, let's say, a very standard neural network, let's say take ResNet, how many layers does it have? Like typically? Lot layers. Like at least 17, 18 layers to 50 layers. And if you look at the parameters, they are coded in millions.
Millions,
yes. There is a 170 million parameters at least for a standard neural network. But then the neural network that we just showed you had like some 2 layers with some neurons implementing its like. Why did we not spend did we not like capture the space of SOC curve, basically the entire function completely, just by using only these many parameters. But then, like that's the whole point of it. The thing is, the problem statement is not just to get the most accurate neural network. That can be easily done. Like if you apply more code layers, but the most important thing is to reduce the footprint as much as possible. Footprint is basically the memory space, the network office. Okay, let's say you have a very big neural network with let's say 17, 18 layers. You can obviously put it in a GPU or run it. Let's say you have a server and let's say a campus and then run the network. That is not what is going to be the platform which is going to be executing. It is actually going to be executing in a microcontroller and a car. Right.
Memory space, so you have to optimize the recording.
Yes. So the problem statement comes down to how would you design a neural network that will give you both accuracy and memory intensive, not so memory intensive. So it comes down to us trying to choose a balance. You understand this is a trade-off, right? If you want more accuracy, you have to use more memory. If you want lesser memory, you have to compromise on accuracy. It's a trade-off. In this trade-off, how do you strike a balance? That is where embedded neural networks come in. So basically, this field of study itself is called edge computing, where you try to move the computing as close as possible to the actual data outputs. Let's say you're getting data and let's say some kind of a small form like has some kind of sensor to give you some output. You don't take the data, give it to a server and compute it there. Instead, you move the compute to the format. You get the compute to the location of data. That's called edge computing. And embedded neural networks are a very crucial part of it. And this is where the distinction comes between a typical AEML program versus edge computing problem. And here the focus is on latency. I'll give you a real example. How can we get an array of, let's say, phase detection algorithms? Yeah, you get an array technique. A lot of scanners are there which can just detect the phases and stuff. So you take a very typical like image detection algorithm, like let's say you know G15 or something. In that, if you take that or not, you can say you run it in a server in a GPU, it will probably give you frames per second. The frame per second is the video capturing. How fast you can do the frames is how fast you can deliver. It will probably give you a FPS of about 30-40 FPS. You guys have played games, you guys know what FPS is. So 30-40 FPS is very decent. Like if you run and if you look at the model you are running, it will also like capture it perfectly. But let's say you take the model and put it in a security camera. Okay, you put in a security camera and see the traffic light. You want to apply that. If you look at the video output, you will be running, but after crossing the first frame, it is that slow. So you only you capture actually what's happening there. That is where it comes down to this is the latency. The term latency refers to how fast the model can give your output data, give it the input data, right? And our aim here is to optimize the latency. So that is why we try to find an architecture that is as small as possible but gives the accurate result. Because that is the motivation, right? So now we move on to explain how we can achieve this, even though let's say you already know the architecture. As an example, let's say you come up with a very big neural network that has let's say some 15 million parameters. Now you cannot find any more length that's smaller than this. Now what do you do? Like you want to apply this, to some kind of a environment, but your model is big, but it's archaic, and you are not able to come up with a model that is like less smaller than this. So is there a solution? Can you guys think of something logical? What can you do?
We can change how the data will be stored. In general, we have 9064. We can reduce it down to 198.
Okay, that is reducing the sample size, reducing the input size, data size. That would mean
how the data will be processed, the matrix that is in the network state. So we can reduce that. We will lose some precision, but we can keep that. That is one way.
How would you reduce the size? Basically, you are saying reduce the tensor length itself. Like reduce the number of neurons used.
No, I am not saying that. I am saying that if you have some data that says we generally store it in INT64, but we can reduce it to INT8 or 4.
Right. Yes. Exactly. So this is not just updating the data that's coming in, but also the small parameters.
Yeah.
So this process is called quantization.
Yeah, quantization.
So you basically do quantization. What you basically do is you have 15 million parameters. You have to go on with it. You have to know that way. What you do instead of okay, how do you guys know how a number is represented in a computer? Let's say I have a number called 15.35.
By zeros and ones.
Yes, it's zeros and ones, but who determines the precision? Like how would let's say if it's let's say number called 15, you can represent it in a 4-bit number. But what is 15.35? How do you represent this?
It's not a lot of precision is not there in the
So what is floating point? That's what the question is.
I think there is an extra value that it takes. I don't actually know that.
Okay. Anyone else can guess what? Let's say I have a decimal number called 15.35. How would the computer know 15.35? So basically what we do is there are some standards called IEEE standards, which basically define how would you store a decimal number in a computer. Okay, how would you store a number with precision in a computer? What we basically do is we have something called we take the 15 first, we first convert the number to scientific notation. We say it's 15.35 and 1.35 to 10%, and then we take the 1.35, that's like basic 1.535, that's basically the number part of it. And then you take this split into 1 and 0.353, and then like you convert this into like binary separately, 1 as binary separately, and then you store the 10 power 1, the exponent as well as the binary separately. You have 3 parts: the real part, the mantissa, and the exponent. And there is a definitive standard that says how many bits should you store for the point after the point. Like let's say 1.33 forever, you just cut off at 1 point, right? That is defined in the standard. So that's how you basically store data. That's called floating point. It's floating point because it is not completely precise. It just keeps on going. It just flows. So in that context, every parameter that you save in the neural network is going to be saved as a floating point. Right? If let's say you train it, you guys know like what are the parameters that you refer to them. Basically the matrix value that you multiply with the input parameters. Is going to be stored as like what? As floating point. Which means that is the value called 1.5 is going to be stored as a floating point 64-bit numbers. So every parameter operates 64 bits. Alright. In that case, what do you do? So you try to, if let's say you reduce the number of bits it takes, every number takes, you will reduce something, but you lose on accuracy because you can't distinguish between 1.535 and 1.534 because you drop out the last digit. Right? Because you're losing accuracy. But what you're gaining at? You're gaining on the very stage. This process, this entire process is called quantization. That's when he said you reduce in 60 in 8, he's referring to the number of bits he used to store a number in the data. Right? So that's the first thing you do called quantization. But you can't manually sit here and literally like reduce the bits of everything number, right? This is not feasible. For this reason, we have something called ONNX platform, which basically takes a neural network, converts it to a standard that's very open to everyone, and then from there it gives it to a TensorFlow like platform, which basically converts it to whatever. Basically, it's a tool to do whatever I said right now. The quantization process is that's all. So for that, just for that, so that you guys can actually go to and try out this to see how the quantization works. I'll show a very small demo as to how this can be done. All of it is another collaboratively Google Colab. you guys all you guys have access to video color. So you guys will be able to do what I say right now in your homes. Okay. I will show that this one demo. Yeah, so we will be now to this. Do you guys have any doubt here? Do you guys have any even if
You don't have a background.
sorry?
Have a background also you feel.
Oh, background here say.
Your background, yes.
Right. So yeah. Sorry, should introduce others. So I am Harish. I am studying electrical engineering in my third year right now, undergrad. And he's Prajwal. He's electrical engineering second year. She's Laurika from EP engineering physics. She also from second year. So we are basically from a team called Raftar. I covered that in the presentation. What we do and why is it relevant? What is the context here? Yeah, coming to the model. So firstly. Okay, so firstly, I said two things, three things to know. I'll tell you three things. Three tools I'm going to introduce you. Tool number one is called Torch. You guys have heard of PyTorch. PyTorch is basically a tool that's developed by Facebook to train neural networks. Okay, it's a very easy tool to use. Tool number two is called ONNX, Open Neural Network Standard, which is a tool again used to exchange neural networks. Let's say I have a neural network and I developed some other program. You have another neural network. How do we exchange the models? You basically convert it to ONNX, give it to you, you will be able to use it. As simple as that. The third tool I will tell you is TensorFlow. TensorFlow is a competitor to PyTorch, but is developing tool. It's the same tool used for developing training neural networks. Okay. All of these can be learned very quickly. Just go home, just Google what all of these are. You can easily.
So why you used PyTorch and TensorFlow together?
Yes, very good question. Yeah. So the basic thing is this. So the way these tools are built, TensorFlow is mostly used for ready-to-use applications. Let's say you have something standard that's built, you want to deploy it. All industries will probably use TensorFlow. But it is not the case with the research. Academicians.
For that we use PyTorch because
Yes.
we can get at the very code level and do
Exactly. So in PyTorch, you have customizability, where you basically can go to every single layer and want to tune that layer or not. You can do this in PyTorch. So that is why you're using both of it in the same model. So firstly, how many of you guys know Python here? Okay, that's a good number of hands. Fine, I can confidently go to the code. So basically, these are all library imports. I am importing all of them. What I said, like Torch, TensorFlow, ONNX, all of it. We will share the code with you today. So you can go to the code very slowly at your own pace. But this is just to give you a brief intro of what is what. That's it. Scrolling on. So yeah, just doing some defines there. Coming down. Yeah, this is the actual model. So it's a very simple model. You can see the model itself there. It's just a linear layer, two layers, could be layer on each, and the from activation layer, the tan bullet, and then the leaky redo. What is it? You can Google what definition is. Leaky redo is just like a function. After the output of the redo, you pass it to the activation function, and then you again get the output of it, and then you pass the next layer. It's just like a function between every layer. That's it. That's called activation function. Like whoever would have studied it, everyone would know this.
Value and leaky value are somewhat similar.
So they are actually very similar, except the fact that on negative axis, if it's a ReLU, it cuts off the entire. But leaky ReLU has a small slope, and that slope is what you specify as point there. Okay. So this is basically the definition. And then you scroll down, you will see you will see first conversion is torch to ONNX. I have developed the model in torch because I wanted to tune on the parameters. I developed it. Now I want to make it smaller. That's the end goal. End goal is to make it smaller to another advanced device. So you have first convert to ONNX. You convert to ONNX. Further, there is an inbuilt function called torch.ONNX.export, where it converts into ONS format. From there, you get the ONS format, you save it. And then if you scroll further, you will get the ONS to TensorFlow model, where you first take the ONS and then convert it to TensorFlow. Okay. Why TensorFlow? Because the thing I said right, converting the every single parameter to a smaller memory. That tool is only provided by TensorFlow. So that is why you can TensorFlow. Once you come to TensorFlow model, then you can just call this function TF right converter. This basically does whatever I said almost. Like take every single number in the parameter of the model, quantize it, make it smaller, so that you can actually put it in an application of like embedded device. It can give you a reduction of about 90%. Like let's say the model is some 100 KB, you will enter to 10 KB model. For the context, how many guys know Arduino here? Arduino? Yeah. What is the memory in an Arduino? Like you guys know your CPU has some. No, not SD card. Like let's say you take your computer. What's the memory in the computer? No, the RAM. 4 GB. What is the memory in an Arduino? Yeah. What is the memory? No, Accelerator is the name of the microcontroller. So what is the, okay, let's say you have Intel IP core that will have its own RAM built in. Similarly, you take a microcontroller. What is the RAM of the one example is about Accelerator 320. That's a microcontroller. So what is the size of the RAM? Yes, exactly. It's 1 liter, but yeah, 512 KB is a very standard size. 512 KB, not any. You're talking about like 2 GB RAM and you come down to 512 KB RAM. That is why we are putting so much effort into all of this. If your model can run in your 4 GB RAM computer, doesn't mean it will also run in your 512 KB RAM computer. That is why you have to carefully make sure the model, you don't lose accuracy, but you still compress it so that you can run the computer. This is the whole perspective that we are doing. So this will ensure your model, you are now, once you go through this code, you are equipped to take any level that you train and then deploy it in the system. So this is basically the gist of all this. It is everything else.
How PyTorch stores the model and TensorFlow stores the model are little bit different. So how when OS does it happens due to ONX that both model can be converted?
Okay, so firstly ONX defines some standards that basically tries to look at the layers and it has its own definition, right? It converts it to its own definition.
Okay.
Once it takes it and stores it that way, basically what ONX does is nothing else. It just people a bunch of people have sat down and have literally written every single possible layer conversion possible. And once that is achieved, you can convert that control into any model. That's it. That's how ONX is.
It's like a converter in the middle.
Yes, exactly. Nothing else. Nothing more than that. Just a converter. Yeah. So do you guys have any basic questions? Any kind of questions you have? Any random questions you have? Also can ask. Even the startup. This basically is what we are going to cover today. So do you guys have any doubts?
How are you going to share this?
Yeah. So we'll be having a small quiz right now. Just to check if you guys are awake during the entire presentation. There we I hope it's easy. Easy. Yeah, I hope it's easy. And through that we'll get your emails and we'll share the content with you. So you guys can start scanning. Okay, before scanning, if you have any doubts, you can ask me. That's why I've been insisting on doubts. In certain cases, it depends on this. There is no link. Yeah, so coming to who here, the context. Basically, we are a student team in IT Madras. We are called a team Raftar. So, what we basically do is every year we build an electric racing car from scratch. Like not just like buy a battery, buy a controller integrated, but we build from scratch. Like we just purchase this, we build a battery pack, like we build our own motor controllers and we build our own electric controllers. And then we put all of it together over a course of about 8 months, and then we take it to a national competition and international competition. So there is this thing called Formula Student. You heard effort racing, right?
Yeah, Formula Green and Formula Student.
Yes, yeah. So you heard effort rate. So Formula Green know effort racing. So this is basically a student version of F1, where we build an F1 make car. And all of what we have seen right now is just 1% of what goes into the car. Like it is just the entire car as a picture. You take just the battery, in the battery just take the battery management system. In that, take one thing that you estimate the SOC, all of what goes in. So this is the level of stuff that we deal with. And like we have been one of the oldest teams in IT Madras. We've been there for like 11 years. You've heard of ASRS, right? You've heard of Exponent is a similar company in EV. So both these companies came from Raftar. The founders of Asia Energy were a part of this team and they graduated. They went on to found Raftar, found Asia Energy. So like what we basically do is like our aim is to like not just build race cars and then like go to race. Obviously, not necessarily do it. But the most important part of this, like the kind of technology that we research and we find out why is it so that like racing is the best platform for finding automotive like solutions, because in racing you push everything to the limit. So something works and that's it. You obviously work the last in the bucket, right? So that's where we aim. We aim to develop best of automotive technology in racing, and we want to give it to the automotive passenger market. So that's basically what we do as cycling. So our primary aim is to build races. Obviously, that's the aim. That's why we participate. So there's something exciting for you guys. Like we are planning to announce a 2-week workshop, conduct a 2-week workshop in probably this summer soon. On how does data make EV smarter? Like it's just a snippet of the entire workshop. We're planning to introduce a lot more cool things as to how can data and how can software come into picture in EV. Like what is the difference between EV and a CV? It's a software. It's why are EVs considered smarter? Because you have a lot more control and it's more smart. And that is where like we want to introduce, like you go to a glance of what we do at Raftar over all the software, not just this, the BMS, the motor controller, and predictive algorithm, like predictive modeling. Let's say you obviously a car there's a fault installed, you shut down. That's not what we want to do. We want to predict when there are faults, and then we react to it, not just like kind of see once the fault is there, they shut down. So something a lot of cool stuff like this we want to like explore, make it exposed to all those. And we have a 2-week workshop. Who is interested, like you guys can like come join us. We have a lot of fun. How we reach out to you guys is through the email ID given. So we work for you guys. Sure. And our talk is just not fun. We have the car display outside, so you guys can take a look at it. You have a demo outside. So have fun, guys. Bye bye.
Everyone just sit down, we'll have a group photo. Okay?
Wait for a second. This concludes this workshop, and we would like to invite Madam Sir to give a token of appreciation to Team Raftar. Can we have a round of applause?